Right. So we talked about the phase response. We just have seen, okay, the phase response, something similar, which we have seen in our previous also. Magnitude response, something similar, which we have seen previously. And the main thing is that for very much less value as compared to the pole information, we are going to have 0 dB, and very much bigger is going to be either plus 20 or minus 20 log of that ratio, omega over omega p, or whatever the ratio comes out to be. So we write minus 20 slope or plus 20 slope. In case of pole, it will be negative. In case of 0, it will be positive. So let's talk about the phase. That is something which we didn't see before. So the phase, as I just mentioned, we can write A of omega. So for that, the same magnitude response which we have previously, we can write in a similar configuration that this is equal to, for a 0 case, for example, 1 plus j omega over omega z, which is equivalent to, if I want to write, it will be equivalent to tan inverse of omega by omega z. And that makes our life simpler. We know a lot of things about tan. What we know about tan, we can bifurcate into 3 different ranges. If the same thing, if omega is less than omega z, this means, again, just to clarify, this is a plot and this is omega. Okay? Omega z is at a fixed point, meaning this area, which is less than 10 times of this area, meaning if this is omega z by 2, so this area I'm talking about, when omega is less than, very much less than omega z. Similarly, when I'm talking about this area, omega is very much bigger than omega z, I'm talking about this area. The area after 10 times at least of omega z. So here I'm talking about this area. Okay? So that we need to identify that less than meaning and greater than meaning. And also omega is equal to omega z. And we can talk about this area this time. So what is these 3 areas when this first one area, which is this marked here, equal to tan inverse of, let's put the numbers and to get an idea. We said omega is equal to omega z by 10. This means so 1 over omega z by 10 by omega z. Again, we are talking about in terms of approximation. This will be equal to tan inverse of 1 over 10. Tan inverse of 1 over 10, if it will be 0, it will be very much small value. So we can say, okay, this is equivalent to 0 degree. If not 0, it will be 1 or 0.23 some degree, but we are saying it's equivalent to 0. That is the approximation we are using in the Bode plot. Similarly, when tan inverse is equal to very much bigger, we can say 10 times omega z divided by omega z, equivalent to tan inverse of 10. What's happening here? Again, equivalent to very much bigger value, which we can say equivalent to infinity. And this means a 90 degree. And when they both are equal, this time it's not omega is equal to omega z. So both are omega z. This means equal to tan inverse of what is 1. What is this thing? 45 degrees. This time it's equal. So that's something which we can see. The phase I'm drawing to the right, when below, for example, this is 0 degree. Sorry, this is 0 degree. If this is my 0 degree, so it's going to remain at 0 degree. And it will start rising till this point to 45 degree. It will continue rising till this point to 90 degree. And after that, it will start stabilizing again. So here, this point is 90 degree. Here, this is 50 degree, and you start from 0 degree. So for one pole, the maximum angle it can contribute is 90 degree, ramping at very much less value of omega, which is very much less than omega z. and reaching to a bigger value. And for approximation, we can say omega z by 10, starting from omega z by 10, ending till 10 times of omega z. And the angle maximum it can ramp is 90 degree. In case of 0, we have seen it's positive. And in case of pole, it's going to be negative. And here the main issue comes. 0 के केस में तो पॉजिटिव है and pole के केस में negative. And if we have minus 180 degree, this means ultimately our system starts becoming unstable. That's what we need to avoid. But still, we are not touching this point. Let's do some review in terms of plotting. So we talk about the rule of thumb. The rule of thumb is what? But let's draw a simple overall system in terms of magnitude and plot. Rather, I will use this as a reiterating rule of thumb, and I can draw the complete one system here. So if we have again a of omega, which is equal to 1 plus j omega by omega z divided by 1 plus j omega by omega p1 divided by 1 plus j omega by omega p2. Okay. So if we have this one, and some, because we need to know, we don't have numeric numbers, so we need to know something. What is where the omega p1 is lying, where omega p2 is lying, where omega z is lying. So what is given to us is this information that omega z is 100 times of omega p1. This means omega p1 is the dominant pole, and omega p2 is equal to 100 times of omega z. Just this is for simplification. I give this number so they don't interact with each other in terms of angle. When one's angle finished, the other angle starts. So this is the configuration, and I'm going to plot in the next one. So if we want to do the plotting here, I will use the here, so we can just have something. This is for the magnitude. So for the magnitude, I will just, and I'm using 20 log. So just by default, I'm using 20 log. And I'm just marking the markers. This is my omega p1. This is my omega z. This is my omega p2. This is my omega. And at this point is ultimately, which is 10 times omega p1 also is equal to omega z by 10. So just clarify this thing. This is 10 times of omega z and omega p by 2 by 10. Okay, and this point is omega p1 by 2. So you just, for easy, the factor of 10 we are using. Some books, some people use the factor of 5. I prefer factor of 10, so it's more easy for us to divide, I think, factor of 5 than sometimes. So we can talk in terms of decade. This thing. And also we will do the something similar for the angle, the phase response. The phase we can have like this. Omega. Okay. So we can do the markings again. This will be same marking which we just mentioned up. So they will use here. And what else we want now? We want to have markings of angles, minus 45 degree. And I have 2 poles, 1, 0. By the end of overall conclusion, my angle of overall system should be minus 90 degree. That also we need to know this thing. Not clarified, make sure, try to go through why. That's what I'm drawing to minus 180 degree. So let's start with the magnitude plot, and we know those conditions that we draw here. So initially we start with a 0 dB as we know. So here it's a 0 dB scale. Okay. Till omega p1, what's going to be a magnitude? It will be at 0 dB. And again, I'm not bringing that minus 3 dB point, so it will be right. So just like a little bit in dealing with this one, a little bit, it's not that much accurate to draw the line and the stuff, but I will also do, we have last year lecture, which is we draw it on the paper and pencil. I guess I will also upload those content also, and also those lectures, so you can go through those material to if something is not clear at this point. Just to again identify these 2 points are same. 10 times omega p1 is equal to omega z by 100, omega z by 10. Okay, so that's what the given condition, for example. So as the first pole comes, we start having minus 20 dB per decade. Till what time? Till the zero comes. So here it is going to have a minus 20 dB per decade. What will happen onwards? It becomes equal to 0 dB because the 0 will be cancelled by the pole until the second pole comes. So this is going to be a 0 dB per decade. Okay. What will happen afterwards? As we touches the second pole, it will again have a minus 20 dB per decade. So it will continue until another it comes. It will have minus 20 dB per decade. Right. So we can have this configuration from this magnitude plot. I guess magnitude plot should be clear. If you want something, we can also look into it. And also if we want to draw, what is this value? It is 20 dB. So per decade is minus 20. And this point, if I want to quote this point, it is here, which is equal to minus 40 dB. So you can also mention these points, assuming the starting point was 0 dB here. And then it's going per decade. Per decade means after every 10 times the frequency. Something similar now let's do with the magnitude plot. So for magnitude plot, what we know, it will start, the angle will be at 0 degree. So this is 0 degree. Okay. So we know that it will start at the 0 degree, but it's because of the first pole 10 times, it will start going down with a ramp of minus 45 degree per decade. So it will, till this point, it's fine. But as it will reach omega p1 by 10, it will start giving a ride. And at omega p1, it will reach 45 degree. And at this point, it will start reaching this. So here you can say at this point where they both are equal, we will have minus 45 degree. At this point, when it's 10 times, we will have minus 90 degrees. So this is a minus 90 degree. This point is 10 times omega p1. And interestingly, in this point, we are also given this is 10 times of omega z1. So because of this effect, this will start going up. With what angle? With again 45 degrees. So we can so you can easily draw even the ruler these things. And this point is what? Omega z. And what should be the angle here? Again, minus 45 degrees. What will happen? It will continue ramp till this point. What is this point? 10 times omega z. The angle will be 0 degree again. But also interestingly, this point is omega p2 by 10. What does this mean? It will start again going ramp down. So here minus 45 degree. And till where it will continue? It will continue to the point 10 times of omega p2. So till the point 10 times of omega p2, it will go till minus 90. And after that, what will happen? It will remain there until another zero or pole. It sees the things. So it will remain at this point. So you can identify these all points. So the final angle is minus 90 degrees. That's well and good. So till now we did the review of a Bode plot. I will do one example from your book. And then we can see now we talk about something, but still we didn't see the stability. For me, this system is stable, but how we are going to see from this Bode plot, we will just wait for a moment. So I will just do one example from your book to clarify this point. So the example is 12.35. So the example is basically given as a 1 pole and 2 pole system. And what we do basically for a 1 pole system, so it's showing how the 1 pole and 2 system behaves, both magnitude and so it's pretty much straightforward. So I will just quickly do the thing. So 1 pole system, they are saying if you have omega, you start with some frequency, and at omega p1, you can have start decaying down with a slope of a minus 20 dB per decade. And this is your a omega magnitude. Similarly, if you want to do phasor plot of this one or an angle of this one, You can have angle of A omega. Here, this time what you are doing, will start with the some angle which is 0 degree, and we need to identify the point omega P1 by 10. So the angle will be, I'm drawing with the green, the angle will be here at this point, it will start going to minus 45 degree. So this is minus 45 degree, and then it will start till reach till minus 90 degree, and it will stay here. So we have a single pole system. As opposed to if I have a two pole system, what will happen? And those two poles are equally far from each other. If they are equally far from each other, yes, we are okay with that thing. We just have to individually take their role, that omega P1 is here and omega P2 is here. They are separated by at least 100 time difference, the same way which we did with the condition that omega P2 is equal to 100 times of omega P1. If this condition, we are not much affected, meaning we will start from here, we will go till this point, we'll reach till this point, and then the decade will be, here is minus 20 dB per decade, here it will be minus 40 dB per decade. Starting whatever, it's 0 dB or whatever the value you are giving. And if I want to do the phasor of this one, the phasor will be starting with a 0 degree, going till 45, going till 90 degree, going till 135, and going till minus 180 degree till omega P to 10 times of this value. So it's not that much. Let me just draw it. As I'm saying, it's a bit clumsy to draw using this one. So I'll draw here. So this is basically minus 180 degree. As I'm saying, I will upload those last one too, so you can look into the things. And let me mark you the markings here. So this is omega P1 by 10. This is omega P1. This is 10 times omega P1. This is okay. So this one, let's write this one is omega P2 by 10. It's fine like this. And this one is omega P2, and this one is 10 times omega P2. I will just revise a little bit from here. So if we want to have, now our plot will be, we go till this 45 degree, this is minus 90, then we will stay till a small, and then we have minus 45 till here, and then we have till here. So like this. Now that is more clear as I feel. So here, it's minus 45 degree, minus 90 degree, and we have a stay at this point because this condition is above. I will write just. So now we are saying this condition is above. Okay, that's the plot which we can have. So similarly, you can have for 3 plot, and those examples are going to be clear as you will do more by hand. So now let's coming about the stability topic. Now, how Bode plot helps in stability of a system? That's the main thing. So last time you remember we talked about something which was loop gain. What was loop gain? We have this one, A, Y was going here, something was K, and we have something summing, we have here negative, we have X. And we talk about loop gain as K times A. So we have Y over X, which was equal to A divided by 1 plus KA, and KA was called as a loop gain. So that loop gain is very much important. We use this loop gain ultimately to ensure the stability of the system. So we do the Bode plot of this loop gain. We do the Bode plot of this loop gain. And then we try to figure out how the things happen. So before moving forward, let me reiterate again. We have this V out by V in, which is equal to y over x is equal to A divided by 1 plus KA. Okay? So that's what we are all know. A, we have feed forward path gain, let's say, or open loop gain, feed forward gain, and KA is a loop gain. Okay? So if we cut the loop, we saw this is the gain which we are going to have all the time. We saw these all configurations. Now, if we say this is a number 1, and if KA or loop gain becomes -1, what will happen? That's something which we need to bring. Magnitude wise, it's 1. Phase wise, it's become 180. What will happen? Meaning, if I want to write -1 as 1 angle 180 degree, this means I'm writing equal to -1, right? Agreed? And if the Ka have this value, what will happen with the V out by V in? A divided by 1 plus -1 equal to 1 over 0. What will be the output? Infinity. And that's make the system unstable. And that's make the system oscillates. Any angle which is going to be bigger than 180 degree will do this thing. Okay, and that's make my system unstable, and that's what I don't want my system to have. ठीक है, तो ये हमेशा हम लोगों ने अब ध्यान में रखना होगा कि whenever my angle becomes 180 or more than -180 degree, we don't want, or less than -180 the way you want to quote it, our system becomes unstable or the system becomes infinite. If this happens, even a very much small value will become a unstable value, will start oscillating, and we don't do this thing. So this brings us to the notion of condition of stability. Condition of stability, condition, if I want to write. So for stability condition, if now the stability condition is applying on what? Loop gain. That's something important. K times A j omega magnitude is greater than equal, and my angle of K times A j omega, okay, is equal to -180 degree. This means my system is unstable. It will oscillate. Then the negative feedback will oscillate. That is the condition of stability. So for me, if my gain or magnitude of loop gain is greater than 1 and my angle is -180 degree, this means my system is unstable. Okay? So to ensure stability, we must make sure that these two conditions doesn't occur at same frequency. Like the gain should be greater at 1 and at the same frequency my phase -180 degree. This shouldn't occur at the same time. They should occur at a different window. How much different window? But let's define again some further terminologies that will help us in identifying these things. Don't worry, we will do a couple of examples to clarify that point. So here I'm writing magnitude response AK. Okay, KA we write, this is omega. The frequency at which if this is 0 dB, the frequency at which the magnitude response crosses 0 dB is known as gain crossover frequency. Okay, so equal to 1 कब हो रहा है? 0 dB means 1. So this is known as gain crossover frequency. So gain crossover frequency. So this means known as gain crossover frequency, commonly your book is calling it omega GX. Also at the same time, if I want to have a phase crossover frequency, meaning at a frequency when your angle of this KA, ये अगर KA का angle है, that becomes minus 180 degree. So if at any point ये मेरे पास minus 180 degree, whenever the frequency I'm going, so here reaching some point, and the point where omega touches or omega reaches the angle of minus 180 degree, this is known as phase crossover frequency. So phase crossover frequency. So we need to find a condition when the gain crossover frequency and the phase crossover frequency shouldn't meet. Agar ye dono ek, if gain crossover frequency is equal to phase crossover frequency, what's going to happen? You can identify yourself now. The system will oscillate. That's why no. So what we know, what we want them to not occur at the same time. So where we want them to occur? For stability, the phase crossover frequency should be greater than gain crossover frequency. I just show with an example, but let's just think why. Phase crossover frequency should be greater than gain crossover frequency. Gain crossover frequency is what? When my loop gain is 1. At loop gain 1, if my phase crossover frequency didn't come, this means it will be less than minus 180 degree. If it is less than minus 180 degree, my system is stable. But if it is touching the point, in gain crossover frequency is equal to phase crossover frequency, system oscillates. If my phase crossover frequency is greater than gain crossover frequency, this means system is unstable. It's like going to have a positive response and it will be infinite. So we want in all the time our gain crossover frequency to be less than phase crossover frequency. I will show you with the help of a plot, and then we can do examples in the next lecture. So for example, if I have this response and it has this point, and this is my 0 dB point. Okay, this is 0 dB means gain crossover frequency. When so here this one, and I have these 2 points. So I have omega 1 and omega 2, and I want to ask which one will be stable point from omega 1 and omega 2. So this is omega 1, this is omega 2, and then we have 2 more plot points. Okay. So we have to see in the same point of omega. We cannot see different omega points, but let's see this thing. So if I have something at this omega 1, and again, I'm just not like making correct, but let's so. So if, for example, same this is omega 2, and this is omega 1. Okay. So at omega 1, if I want to see my angle, omega 1 is minus 160 degree, for example, and in omega 2, my angle is minus 180 degree. Okay, these omega 1 and omega 1 are same points. Same points. What we can write about omega 1? Omega 1 is gain crossover frequency. You all can see it's at 0 dB. And what we can write at omega 2, it's a phase crossover frequency. Okay. Because the phase is minus 180 degree. Now, what about omega 1? Is it stable or not stable? We can see this thing. At omega 1, my gain is 1 or 0 dB. My phase is what? Minus 60 degree. So at this moment, both of these conditions, kh of omega or a of omega, the way we are using this, ka of omega amplitude should be greater than 1, is meeting, so it's greater or equal to 1. That's fine. What about the other condition? K angle of a omega, is it greater or equal to 180 degree or greater than 180 degree? No. So this means omega 1 is stable. What about omega 2? My Ka of omega is greater than 1, and the phase and omega 2 is phase crossover frequency. This means omega 2 is not stable. So that's why all the time we can directly use this criteria that for a stable system, gain crossover frequency should be less than phase crossover frequency. If this happens, I am fine. If it doesn't happen, definitely I am not fine. My system is not stable. I need to work in my circuit to improve that circuit. So next time what we will do, we'll do example 12.37, example 12.38 to clarify further these points. This we will do next time, but what I would like all of you to do some examples on your own to have clear picture and some examples like 12.36 and 12.35. So you do these examples, and this we will do in the next lecture. Okay. In the next lecture, we are going to have our quiz.